let's move ahead. So this was the basic layout of PLC. Now let's see how the processor works, because unless the processor works, there's no use of inputs and outputs. Processor is the main brain of the PLC. So we have to understand how this processor is working so that we can make our logic accordingly. So what is the first step? We have a startup mode. Now startup mode is the mode which is executed before run mode. Okay, we will see the visualization of startup mode as well. So the first step is process image input memory I is cleared. Now what happened? I will take a pen. Now supposingly these are the inputs. Okay, now the status of this input is stored in some memory. If I say this is a memory block, it stores the information of my inputs. Okay, now suppose if my first input is on, it will take the first bit as 1. If my second input is off, it will make it as 0. If my third input is on, it will make it 1, and so forth. It will note the addresses of all, not the addresses, the status of all the inputs and store that in this memory. Okay, so initially when PLC is on, this is cleared. So everything is made 0. This is what they mean by clear. So process image is cleared. This is what it means, startup mode. Okay, so wait. Now the next is output are initialized with the last value. Now this is a little complicated to understand, but what happens, suppose if your PLC goes off and then you turn it on. So in the startup mode, the status of outputs which are reserved in the last cycle when PLC was off, that will be initialized. Suppose you have a PLC and you turn it on, you are executing some process and there's a power failure and you turn off the PLC. Okay, so the PLC goes off. Suppose right now I execute some inputs and I turn off the PLC. So what I'll do is I will just unplug my PLC from here and this goes off. So some output was going on, output was running, but it goes off. But when I turn it on, it will store the value which was at the output and it will just save that value. Okay, so outputs will be initialized again with the last value, but this will happen only if you have retentive memory in your logic. Now what is a retentive memory we'll understand later, but for an instance you can understand there are some memory which are not reset even if the power goes off. Okay, when the power come back again, those bits retain their information and those get turned on again. Unlike general memories. In general memories, these are volatile, but retentive memories are non-volatile. You have to manually reset them. So if non-volatile memory is used to run the outputs, those outputs get initialized again with the last value. Okay, this is the second step. Third is any startup logic is executed. Now we have a special startup logic block in our PLC, which is created by startup bits. Now there are some special startup bits which are executed before the run mode. So this may sound a little complicated, but we'll understand more when we move to programming of the PLC. So there are some startup logic which are executed before run mode. So that is executed in the third cycle. Okay. Now next cycle, state of physical input is copied to iMemory. Now what happened in that case? So what we were doing is initially this memory was cleared. Okay. Now in the next step, whatever input is on, if my third input is on, so it will be written in my memory now. So all the input status will be updated in my memory. So now this status is because of my inputs. If my input is on, this will be on. So PLC has a dedicated memory to store the status of my inputs in my memory, and this memory is called process image input. This is the memory which stores the status of my input. Okay, so that PLC can, while executing the logic, PLC just read the status of these memory, not from the physical input, because this reflects the status of my input. So this is a memory inside. You can also access this memory. So state of physical memory is copied, and Next is any interrupt present are queued to execute. Now, if you know interrupts are some special instructions which has higher priority over normal scan cycle of PLC, which means these can be executed without taking care of PLC scan cycle. Now, what happened in a scan cycle, PLC execute a logic in some certain time, let's say for 5 milliseconds. But if interrupt is executed, it will not wait for 5 milliseconds, it will execute immediately. So these are queued. These are not execute, but these are lined up for execution. These will be execution in the run mode only, but these are lined up in startup mode to avoid any delay. So at last, writing of process memory queue is to physical output is enabled. So just like we have this memory for input, we also have similar memory for the output. So let me take a different color here. Yeah, maybe this one. So these are my outputs, and these output also have some memory in which we store the status of the outputs. Just like we have status for the inputs, we have status for the outputs, which are written here. So this is enabled. This is not executed. This is just enabled. Okay. Here things are being executed. The input is stored in the memory, but here it's not stored in the memory. It is just enabled. Okay. So must know that. Then we have a run mode. Then comes the run mode. So we'll also see how the startup mode execute. In the next slide, I'll show you different status of the inputs, and I'll show you the startup mode. There's a blinking of light. Then you have a run mode. So startup mode is before the run mode. So in run mode, queue memory is written to the physical output. So now what happened when PLC logic is solved? Suppose you have some status in the input. Let me take a different color. Okay, maybe green one. Suppose you have some status in the input and you have some logic in your PLC. When this logic is solved, the answer of the output is stored in my process memory. Okay, so it says queue memory is written to physical output. When this memory has some answers in run mode, it could be 0 or it could be 1. Okay, because it's a digital output, it's 0 or 1. This is written to the output. Now the output will either have a voltage or it will not have a voltage. If this output has 1, it will give the voltage, which could be 24 volts or line and neutral, depends on what you connect to the common. Or if this output is 0 in the process memory, it will not give any voltage, it will be open circuit. So in the run mode, the first step is queue memory is written to physical output. So whatever information you have in the memory of output is given to the output terminals. This is what it means. Okay. Next is state of physical input is written to I memory. Now again, state of physical input, this input is again written to the I memory. This is the same memory. Okay. Then logic is executed. Again, this logic is solved. Self-text diagnostic is performed. Now, if you have any error in your PLC, it will diagnose it and it will indicate that in your computer or in your HMI. So there's a diagnostic function which is performed by itself. You don't have to make a logic for that. It will be performed by itself. So if there is any error in the inputs or outputs, it will be indicated. So then again, it goes back to the first step. So the logic is executed. After diagnostic, output is written to the physical output. Again, it will read the input, solve the logic, gives the output, read the input, solve the logic, gives the output. This cycle keeps on repeating. And this cycle is called scan cycle. This is the scan cycle of a PLC. Now this scan cycle depends upon 3 things. Number 1, how many inputs do you have? If you have a large number of inputs, PLC will take a lot of time to read those inputs. If your logic is small or large, it also depends how much would be the scan time. So it depends upon the length of the logic. It also depends upon the number of outputs it has to turn on. So number of input and outputs and length of the logic defines the scan time of a PLC. And in this scan time, interrupts and communications are processed during any part of the cycle. As I told you, interrupts does not depend upon scan time, and communication means to read and write the output in some HMI or some external communication with RS-485 that is executed in any part of the cycle. So this is basically how a processor works in any PLC. This is about specifically about S7-1200, but this is generally in all the PLCs. Okay, so let's proceed the operation mode. Let's see in more detail about the operation mode. So we have initially the run mode. Now in run mode, you have this green LED on. As I showed you in my video as well, this is my run mode. So this green LED is on. Okay, so in run mode, scan cycle is executed repeatedly. As I told you in the last slide, interrupts can occur and process at any point within the process cycle phase. So interrupts can occur as well. Now we have a stop mode. In stop mode, you have this orange LED. Okay, now in stop mode, there will be no scan cycle. PLC at stop mode, it will not execute the program. And you can also download a project when PLC is at stop mode. You cannot download the project when PLC is run mode in some special conditions. Then you have startup mode. Startup mode is for the startup logic, which I explained you in the last slide. Now to see how the startup mode occurs, I have a small video here. If I click play, when PLC runs, you will see this will blink. Now this is the startup mode. So this is the startup mode going on, and now it will go back to run mode. So it goes to green. So when it blinks, that is the startup mode, and automatically it switches to run mode. This is how, these are the three different modes of PLC. And you can control these three modes using the software in TIA, which we'll see now for the lessons. You have buttons run, stop, and M reset. This is for M reset is for resetting the memory, and here you can change the status of your PLC from run to stop or stop to run. Okay, these are the operation modes of your PLC. A fact which says you can download your project only when the CPU is at stop mode. Okay, not otherwise. So let's proceed to the next slide, which is data storage in PLC. Now data storage means how you can store the information in PLC and how PLC process the data in its memory. So we know that the single smallest bit of information is a bit, which is a binary digit bit. So it has only two states, either 0, which means false, or not true, or 1, which is true. Okay, so let's see the structure. For that, I have an example which shows that we have a light switch. Now if you know, we have a light in our room. So if light is on, we can relate that to true. If light is off, we can relate that to false. So this is how you can relate that. Something which is off is 0, something which is on, it is true or 1. This is how we process by digital bit 0 or 1, because PLC does not understand the characters as it understands the digital bits. So PLC doesn't know what is light on, but it knows what is 1, which is true, and 0, which is false. So what is the data structure? Now you can see that this is 16 bits here, starting with 0, 1, 2 up to 15. Now this is the 1 bit number 1. This is second bit, third, fourth, fifth, sixth, seventh, and so on. Now collection of 8 bits here from 0 to 7, this is called byte. 1 byte. 1 byte has 8 bits. Okay, and the collection of 16 bit, which is called word, this is 16 bits, and that is equivalent to 2 bytes, because 1 byte is 8 bits, 2 byte is 8 multiplied by 2, which is 16 bits, and we call it as word. So how this value comes, when you write 2 raised to the power 16, you will have this range. So that is how you get the value. And how much value you can store in 8-bit, that is 2 raised to the power 8. Okay, if I show you my pen, if you take 2, take the power of 8, which comes out to be 256. So this is the range of my 8 bits. Okay, if I have a value more than 8 bits, I have to use a word. I have to use more data of my PLC, more memory of my PLC. So that's how you store the information. It's very basic: bit, byte, and word. Okay, so this is one of the facts you can read here. Now data types supported by the PLC. Now what are the data types which is supported? So this is in more details. We have a Boolean. Boolean is same as bit, 0 or 1. So range is 0 or 1. So Boolean is also true or false. Size is 1 bit, it's 0 or 1. Then we have byte, which is 8 bits. So in bytes we have 16. This is representation in hexadecimal, 00 to FF. Now this FF is a hexadecimal representation of 8 bits. Okay, you must understand this is a very basic of digital control. to represent something in decimal or hexadecimal. If I'm using hexadecimal, I'm using 16 and this window sign. Word is 16 bits, so if 4 times, it's 16 bit. 32 bits, it's double word, so you have twice the value of 16 bit. Then you have a character, which is 8 bit, just like my byte. Then you have int, which is 16 bit, just like the word. Double int is similar to double word. This is the conversion of hexadecimal to decimal. Then you have real. Real means when you have something in decimal value, you can use the real data type. So this defines the data. If your value is coming in integer, you can use integer. If it is in real, you have to use real. Otherwise, you will not get this fraction values. Okay. Now, we will continue this video in the next lesson to understand the memory area and some demo sample programs.